Have you ever wondered how water skiers walk on water?
Oops. Or how liquid travels up the face of a napkin?
Have you ever wondered how I did this in my hands?
Have you ever wondered how water gets from far below ground to the tallest heights of trees like this? We're here today to talk with you about surface tension and capillary action.
The phenomena of capillary rise was believed to be first recorded by Leonardo da Vinci. After da Vinci, there had been a couple of other scientists, including Isaac Newton, who were also interested in the phenomena. All of their hypotheses were based on the intermolecular attraction force. However, they failed to give explicit explanation to the phenomena. The field of study was pushed forward by Alexis Clairaut and von Sackner. They were the pioneers of considering the attraction force with liquid itself, and von Sackner was the first one who introduced the idea of surface tension, which had a very important effect on the development of the theory. In 1802, John Leslie gave the first explanation of the rise in a tube with regard to the intermolecular force. Finally, in 1804, Thomas Young founded the theory of capillary phenomena on the principle of surface tension, and noticed the constancy of the contact angle between solid and liquids. In 1806, Pierre Laplace first deduced the theory entirely by mathematical calculations. Since then, the development of the theory shifted towards a mass-based direction. In 1830, Carl Gauss first aggregated the force between the particles and bring up the idea of potential energy of the system. After all these great contributions from previous scientists, the main structure of the theory was set.
The value of surface tension is temperature dependent and different for each fluid. The SI units of surface tension are newtons per meter. Surface tension differs between fluids because the strength of intramolecular forces depends on the chemical makeup of a particular fluid. The intramolecular forces in water are much stronger than oil because of the high polarity due to the hydrogen bonding. The fatty acid makeup of oil is nonpolar, causing the intramolecular forces in the oil to be mostly due to London dispersion forces. These are quite weak compared to hydrogen bonding. The comparative strength in the attraction between the water molecules and the oil molecules can be observed by noticing how much harder it is to drop the oil onto the penny dome than to add a drop of water. Both the oil and water are able to create a dome over the penny without spilling over the side due to the surface tension acting around the edges of the dome where the water meets the air. The water, however, is able to maintain a much larger dome with more droplets because it has a higher level of surface tension.
In this demonstration, we show the force of surface tension on the paperclip resting on the surface of water. Throughout the fluid, the water molecules form hydrogen bonds with their neighbors. At the water-air interface, since the water molecules are exposed to the air on one side, they have fewer neighboring water molecules to bond with, thus forming stronger bonds with their neighbors. Tangent intermolecular forces between water molecules create a surface that exerts a normal force on the paperclip, shown here. With the paperclip at rest on the surface of the water, one can assume static equilibrium and draw a free body diagram of the paperclip. You can start by drawing all the forces acting on the paperclip, starting with the weight of the paperclip, and then you can draw F, which will be the surface tension, the force of surface tension acting on the water's surface. And then lastly, you can draw R, which is the reaction force acting on the needle. So then you can balance all the forces in the y direction, which will be R1 cosine theta. Theta is the angle, the contact angle, plus R2 cosine theta minus the weight, and that's all equal to 0, assuming static equilibrium because the paperclip's at rest at the surface. And then due to symmetry, we know that F1 is equal to F2, and that's also equal to the length, which is the L is the length of the contact line on each side, or the entire surface of the paperclip. So, yeah, the entire line of the paperclip. And then that's multiplied by the stress of the paperclip on the water. And substituting these into the original force balance equation, and then to find the maximum weight of the paperclip to guarantee, and in the case of static equilibrium, you can assume that the contact angle for the surface tension is 0, and therefore the maximum weight of the paperclip is equal to twice the length of the total length of the side of the paperclip times the stress of the paperclip on the water.
In this comparison, we can see capillary force in action. On the right side, we can see water climbing up the surface of a beaker and glass rod. This is because of the adhesive attraction between the water and glass molecules. This is absent on the left side, where we have added a hydrophobic layer of oil to the glass surfaces. Here we have capillary action for both water and oil in small diameter tubes. We ran several trials and measured the height of the fluid's rise to obtain an average. For water, we got 1.21 centimeters, and for oil, we got 1.11 centimeters. Now we will use this force balance equation to solve for theoretical height to compare with the experimental values we measured. With some expansions and cancellations, we can now solve for height h with this equation. Plugging in numbers now to calculate values, including a small angle approximation of theta equals 0 for the contact angle, we find 2.6 centimeters for water and 1.2 centimeters for oil. The oil value is pretty close to what we measured, but the water value is over twice what we got. Why could this be? It turns out the value for surface tension that we use applies to pure water. The value for tap water can vary quite a bit. Using a value found in the textbook, the calculation returns a value closer to the experimental value we found.
After 1 week, both plants have lost a certain amount of water. Since the bottom of the plants were wrapped, most of the water is lost due to transpiration. In order to draw the water from the soil to the leaves, plants utilize a combination of capillary action and partial pressure difference to maintain the water inside. The capillary action is induced by a mesh grid of cellulose which takes up a very narrow space between each molecule within the plant. In general, this process is like inserting a tube with a very small opening into water, which according to previous math we calculated, means that there should be a high water rise.
Thank you for tuning in.
Till next time.
Have you ever wondered how I did this in my hand?
No.
But I'm gonna show you anyhow.
All right, cut.